In the previous video, we looked at comparing the mean pulmonary function of 6 different groups based on their smoking status. We were able to compute the sum of squares for the treatment and the sum of squares for the air, which then led to the F statistic, which we got, which was 57.99, with a corresponding p-value that was less than 0.001. And we were able to reject the null hypothesis that all the group means were equal. That meant that the alternative was at least one of the groups had a mean that was different from the others. But the question is, which group means are statistically different from each other? We have the mean, for example, of the non-smoking group, which is 3.78. Is that statistically different than the mean from the passive smoking group, which was 3.3? Are either of those means statistically different from the heavy smoking group, which was 2.59? The answer to how to figure that out is to perform what is called a post hoc test. This is a test that you perform after having done the test for ANOVA. There are lots of different kinds of post hoc tests, so I'm going to explain one of them to you called the Bonferroni method. And the Bonferroni method is the easiest one for me to explain. So recall that ANOVA allowed us to simultaneously compare the group means in order to reduce the error from multiple pairwise comparisons. In this situation, we had two notions of type 1 error. We had the experiment-wise error, which was for the simultaneous comparisons. And then we had the component-wise error, which was for the pairwise comparisons. For example, we saw that if we wanted to do pairwise t-tests for our smoking example, that we would have 15 comparisons that we would have to make. And we found that the probability of at least one type 1 error, which we would call the experiment-wise error, was 1 minus 0.95 to the 15th power, which was about 53.7%. And so we saw that even though we tried to restrict ourselves to only a 5% type 1 error for the component-wise error, that the experiment-wise error ended up being 53.7%. So now we want to kind of generalize that. Okay, so I want to find the experiment-wise error, which I'm going to write as the probability of at least one type 1 error. And we saw that that was equal to 1 minus the probability of making no type 1 errors. Now, the probability of making no type 1 errors was 1 minus the component-wise error. So this is the probability of no type 1 error from a pairwise comparison. And we assumed that those pairwise comparisons were, we assumed that they were independent. And so we took those to the 15th power when we were doing 15 comparisons. So we'll take them to the C power here. Okay, So we now have a relationship between the experiment-wise error and the component-wise error. Now for small values of alpha, we can say that 1 minus the component-wise error to the c power is approximately 1 minus c times alpha component-wise. Okay, this is done using a linear approximation or a first-order Taylor series, if you like. We're saying that 1 plus x to the c power is approximately 1 plus c times x. Therefore, we can find a relationship, a more simple relationship between our experiment-wise error and our component-wise error. So our experiment-wise error is 1 minus c times alpha sub cw. So in other words, that's going to be just c times alpha sub cw. And that gives us an approximate relationship between experiment-wise error and component-wise error. Now that we have that, what that says is if we don't want our experiment-wise error to be any larger than some amount, then we can make our component-wise error smaller in order to make sure our experiment-wise error doesn't exceed that amount. We can make our component-wise error equal to our experiment-wise error that we desire over the number of comparisons. So in other words, we can run these t-tests for various pairs at a really, really small alpha value. And if we do that, all of the errors will add up so that they don't go over our alpha that we desire, maybe 5%. So this is a conservative estimate, though, for the component-wise error, because we assume that the pairwise comparisons were independent. You'll recall when we did 15 comparisons, we got an experiment-wise error of 53%. But in actuality, when I showed you a table, if we considered the fact that they're not independent, it would only be 37%. So we're actually making our component-wise error a little bit smaller than we need it to be, but we're making our component-wise error a little bit smaller than we need it to be, but that's okay because at least it's a conservative estimate and we won't go over our desired experiment-wise error. Okay, so what we're going to do is now we're going to conduct essentially pairwise t-tests. We're going to test all the different possible pairs, for example, of the smoking groups. So at this point, we're going to make the significance level for these pairwise t-tests equal to the experiment-wise error divided by c. Now, we said that the standard deviations were all approximately equal. So just like when we were doing the t-test for two different populations, we're going to consider it a pooled standard error. And if you go back and you look at our pooled standard error formula, you'll see that it's exactly the same as the formula for our sum of the squares of the errors. Okay, so our pooled variance was the same as the formula for the sum of the squares of the errors. And so that means that our pooled standard deviation is going to be the square root of the sum of the squares of the errors. Okay, in the cases before, we only had 2 standard deviations. Now we're finding a weighted average of many standard deviations. Okay, so that makes the standard error for each pair. If we look at it, we can think about it as being the square root of our pooled standard error squared over n1 and our pooled standard error squared over n2, or it's very similar to the formula we had before, which is the pooled standard error times the square root of 1 over n1 plus 1 over n2. The only difference is how we got the pooled standard deviation. The way that we did it in this case is we used all of the standard deviations from all the groups, whereas before we would have just averaged for the two that we were comparing. Now, the degrees of freedom for this problem is going to be the degrees of freedom within. So that is going to be the denominator degrees of freedom. And that degrees of freedom for the denominator we saw was n minus k. And then what we can do is we could compute confidence intervals for all of our pairs of groups. And so we would take, for example, y1 bar minus y2 bar. And then you would add t sub alpha sub component wise over 2. And then you would do s pooled times the square root of 1 over n1 plus 1 over n2. And that would be the confidence interval for one of those pairs. Now noticing that our t statistic or t value comes from a much, much lower significance level than we considered before. Okay, so let's look at this for our specific example. We're going to conduct a post hoc test using pairwise comparisons for the smoking data. Okay, so S pooled is going to be the square root of our mean square, which is 0.636. And I'm pretty far along into this, so I'm going to tell you that I actually made a mistake here. This is supposed to be the mean squared error. Okay, so the S pooled is going to be the square root of the mean squared error. Okay, so S pooled in this case is the square root of 0.636, and then you'll see that that's 0.7975, which you can see looks like it would be the average of the various standard deviations that we had for the groups. Okay, the degrees of freedom in this case is going to be 1,044. And our pairwise critical value that we're going to consider is going to be 5%, but then we're going to divide that by the number of comparisons that we have to make for 6 groups, which was 6, choose 2. So that's divided by 15. So we're going to look at a component-wise error of 0.003333. Now what I've done is I've decided to do some pairwise comparisons, but instead of doing all 15, I decided to do just the nearest neighbor pairwise comparisons. So I'll go back and show you the data real quick. And for the data, you'll notice that 3.78, the non-smoking group, actually was closest to group 3, the non-inhaling group. Then groups 2 and 3 were closest together. And then groups 2 and 4 were closest together. Groups 4 and 5 are closest together in terms of their sample means. And then groups 5 and 6 were closest together. So those are the comparisons that I'm choosing to make. So in this case, I'm going to compare, say, groups 1 and 3, the non-smoking to the non-inhaling. Okay, the difference in the means turned out to be 0.46. I compute the standard error for that, which was 0.1261. And then I computed a t-statistic, which was 3.648, which gave me a p-value 0.0003. And then I also computed the confidence interval, which you'll notice does not include 0. That means there's a statistically significant difference between the non-smoking group and the non-inhaling group. And so I repeated this with all the different nearest neighbors. So you'll see that between the non-inhaling and the passive smoking group, there's a large p-value, and so there's no statistical difference. Between the passive smoking group and the low smoking group, okay, that's got a p-value of 0.38, and so that's not statistically different, okay? But there is a statistically different difference between the low smoking group and the moderate smoking group. Okay, that has a p-value of 5 times 10 to the minus 10. And then it just misses short the moderate smoking group and the heavy smoking group. There's not a statistically significant difference. Okay, the p-value is 0.0795. Okay, and what's nice is I can arrange these on the graph that you see below. And what I've done is I've plotted the means for the heavy smoking group, moderate smoking group, etc., all the way down to the non-smoking group. And then you can see the differences between those groups. The non-smoking group is statistically different from, say, the non-inhaling group. And because it's statistically different from the non-inhaling group, and then the other two groups have an even smaller mean, then it's statistically different from all three of these groups. So that mean is different for the non-smoking group than it is for all three of those groups. And then those three groups, I put a line over them because to signify the fact that they all are about similar. We cannot accept the null hypothesis, but there's not a statistically significant difference between them. But there is a statistically significant difference between those three groups and the heavy smoking group and the moderate smoking group. The heavy and moderate smoking groups, I put a line over them to signify that there's not a statistically significant difference between those two groups. So what you can see from this graph is essentially we have three groups that came out of this post-hoc test. The non-smokers are different from all the other populations. The non-inhaling, the low smoking group, and the passive smoking group are not statistically different from each other, so they form a little group. And then those are separated from the moderate and heavy smoking groups, which are not statistically different from each other. And this gives us a nice interpretation of our data. Okay, so that's why you'll hear conclusions that came out of this study that said that passive smoking, just being exposed to secondhand cigarette smoke, was as bad as smoking pipes in the non-inhaling group or smoking 1 to 10 cigarettes per day. Now that's a little bit misleading because that's accepting the null hypothesis, but you can say it's not statistically different from the others. And this is when they started putting together a lot of different laws about smoking to reduce the risk of secondhand smoke.